So we're working on some material from Unit 910, and this is boxes D and E, and we're going to look at some rules for differentiation. Now, in the last lesson, we looked at the definition of a derivative and how you can determine both the value of the derivative at a particular value of x, or a function that represents the derivative of the function that you had originally, using the definition of the derivative. And the definition of the derivative that we had was that if our function was, our original function was f at x, our derivative was f primed at x, and we calculated the derivative by taking the limit as h goes to 0 of our function evaluated at x plus h, subtracting the function evaluated at x all over h. Okay? We take the limit of that as h goes to 0, and that gave us our derivative. And we called this finding the derivative from first principles. So if the question asks you to find the derivative from first principles, you want to use this approach right here. If it doesn't say from first principles, then what you want to be able to do is find the derivative by the most efficient means possible. And that's what we're going to look at today. We're going to look at a number of algebraic shortcuts that can let you go from a function to its derivative without having to do all of this mess up here with the limits. And that's going to be the key to the rest of this course, is there's a lot of differentiation rules. You're going to need to know these rules and know how to apply them to find derivatives and use those derivatives to solve problems. So let's just jump right in here. So as I said, we can use that definition, or we can use some algebraic shortcuts. And we're going to look at 5 rules here today that are the 5 rules that you're going to need to know for this unit. So the first rule is pretty straightforward. It's called the constant function rule. So if you have a function, f at x, which is just equal to some constant c here, the derivative, f primed at x, is going to be 0, always. So for example, let's say our function is f at x equals 5. Okay, just a number. That number is a constant. My derivative, f primed at x, is going to be 0. Okay. And if you think about this one, this kind of makes sense. If we visualize what the graph of f at x equals 5 is going to look like, if we draw our x and our y-axis here, f at x equals 5 is a straight line, a horizontal line, passing through y equals 5. The derivative represents the slope of that line. Well, what's the slope of a horizontal line? The slope of a horizontal line is 0. We covered this way back in grade 9. So any point you go to, any value of x, the slope of this line is always going to be 0, so the derivative is always going to be 0. Okay. A little trickier is our next one here. This is called the power rule. And we use this if you've got a function that is x to some power, okay, to some exponent n here. Okay. And I'll just move this up a bit. So if our function is f at x equals x to the n, the derivative, what we do is we take our exponent n and we're going to bring it down so it's out in front of the base x. So we're going to have n times x. And to get our new exponent up here, we subtract 1 from our old exponent. So if our original function is x to the power of n, the derivative of that is n times x to the exponent n minus 1. So for example, if our function is x to the power of 5, the derivative, f primed at x, is going to be, well, we bring down the 5 out in front, 5 times x to the power of 5 minus 1, or 5 times x to the power of 4. rule number 3 here. The constant multiple of a function. So let's say we've got a function, f at x, which is some other function, g at x, multiplied by a constant. And again, we'll use c as our constant again. And I'll put a little dot there to reinforce that we are multiplying there. If we want to find the derivative of c times g at x, or the derivative of f at x, the derivative here is going to be just that constant, c, times the derivative of that function. So c times g primed at x. So let's do an example over here. Let's say our function is 7 times x to the power of 5. Or we've got the function 7x to the 5th. We can look at this function as 7 times the other function, x to the power of 5. Well, what's the derivative of x to the power of 5? We did that in the previous question. So the derivative of x to the power of 5 is 5x to the power of 4. So the derivative of this whole thing, f primed at x, is going to be this constant 7 times the derivative of that sort of inner function, x to the power of 5. So our derivative is 35 x to the power of 4. Right? Makes sense so far? All right, so that's rules 1, 2, and 3. Rules 4 and 5 kind of go together here. They're called the sum and difference rules. And all that this means is that if we have a function, h at x, which is made up by taking two other functions and adding them or subtracting them, so f at x plus or minus g at x, the derivative of this function, h primed at x, is found by taking the derivatives of these individual functions and either adding them or subtracting them. If we were adding them originally, we add the derivatives. If we were subtracting them originally, we subtract the derivatives. So let's say our function is 3x to the power of 5 plus x squared. We can think of this as being made up of two smaller functions that we're adding together, 3x to the power of 5 and x squared. So to calculate our derivative here, we can get the derivative of each of those and then add them together. Now, so what is the derivative of x squared? Well, 2x, right. We just have to apply that power rule. Bring the 2 out front, subtract 1 from the exponent, we're left with an exponent of 1. We have to do the derivative of 3x to the power of 5 here. What's that going to be? Yeah. We bring the 5 out front, we can multiply it by the 3 to get 15, and then we subtract 1 from the exponent, x to the power of 4. So there's our derivative, 15x to the power of 4 plus 2x. Okay. So those are the 5 rules that you need to know to work your way through this unit here. So what I want to do now is just take a look at a couple of somewhat trickier examples here. And yeah, I've said there's a bunch of examples here. There's actually 4 examples that we're going to take a look at. And I think they get progressively more challenging here. Let's take a look at the first one. We've got y equals x to the 8 minus x to the negative 8. Okay. Let's see. I've been using the notation f primed for the derivative. We can also use dy dx. I think that's the textbook uses that a fair bit, so we'll just throw that in here. So how can I take the derivative of this function here? What do I need to do?
Take the derivative of an exponent function, so 8x 7.
Yeah, so I'll get 8 out front, x to the 7th there. And then I got to use that subtraction rule here, so I'm going to subtract from this the derivative of that second term there. So the second term is x to the negative 8, so we take the derivative of that.
Negative 8x negative 9.
Yeah, so we bring down the negative 8, and then we subtract 1 from the exponent, give us negative 9. And then from here we can simplify it. We can say 8x to the 7th plus 8x to the negative 9. And if we really want to, because this is a negative exponent, we can turn this in, we can put it into, change it into a positive exponent and put it down in the denominator of our function here. So this could be 8x to the 7th plus 8 over x to the 9. Usually, sometimes you'll leave it like this, up here with the negative exponent. Sometimes you'll change it down to like this, depending on what you want to do with the derivative as your next step. Okay. All right, let's take a look at the next one here. F at x equals x plus 3 squared. Now, I think it's in the next unit, we'll look at another rule for taking the derivatives of expressions like this. But for this unit, using just these rules that we looked at on the last page, what do you think you need to do first in order to take the derivative of this function?
Put in the square.
What do you mean by that?
Like factor out the expression.
Not factor, but the opposite to factoring? Yeah, expand. So let's expand our expression first here. So that'll give us x squared plus 6x plus 9. Okay. Because now we have 3 terms added together, so we can apply the sum rule by just finding the derivatives of each of these terms individually. And each of the terms that we have, we can use either the power rule or the constant rule to get the derivative of. So f prime at x is going to be, well, let's see, what's the derivative of our first term here? 2x, yep, bring the 2 out front, subtract 1. What about 6x to the power of 1? What's the derivative of that going to be here? Well, let's see. It's 1, so we bring the 1 out front, so it's 1 times 6x. We subtract 1 from the 1, which is going to give us an exponent of 0. But x to the 0 is just going to be 1. So we're just going to be left with the 6 there when we simplify. And finally, the last term here, the 9, is just a constant, so the derivative of 9 is going to be 0. So simplify this. 2x plus 6 is our derivative.
Wait. Yeah, I understood your first.
Okay, so we fixed that to make it a little bit more clear. Let's look at our next example here. We've got y equals 6 over x cubed plus 2 over x squared minus 3. There's something we should do to this one here before we try to take the derivative, just to rearrange this thing. If we have those exponents down in our denominator, we should probably bring them up into the numerator and change the signs on them to negative. So this would become 6x to the negative 3 plus 2x to the negative 2 minus 3. Now we can go ahead and find our derivative. So if our original function is y, for our derivative we'll just say y primed. And we can go, now we can just apply those 5 rules that we've looked at before, doing this term by term. So we'll have negative 3 times 6 is negative 18. X to the negative 3 minus 1 is negative 4. Our next term is going to be negative 2 times that 2 out in front. So we'll get negative 4x to the, subtract 1 from the negative 2 is negative 3. And our last term is a constant, so it's just 0. And if we wanted to, again, we could change this to negative 18 over x to the power 4 minus 4 over x to the power of 3. Fix that x up. Okay, our last example here. We've got f at x equals root x plus 6 times the root of x cubed plus root 2. And again, we should probably rewrite this one in a slightly different form. And again, we want to use a form where we can apply the power rule, or the power law here. So we want to change these square roots into exponents. So root x is x to the 1/2. So for our second term here, we're going to have 6 times x to the 3 over 2, because we're taking the root and we're cubing the x as well. And this last term, I can just leave it as root 2 because, well, it's just a constant, and we know that when we take the derivative, it's going to go to 0, so that doesn't really matter. So let's take our derivative here, apply our power rule, bring down the exponent, so this is going to be 1/2 times x to the, I'll just write this in, 1/2 minus 1 is going to be our new exponent, plus we're going to have 6 times 3 over 2, bringing down that exponent, x to the 3 over 2, again, minus 1. One half x. See, 1/2 minus 1 gives us negative 1/2. And 6 times 3 over 2 is 18 over 2, which is 9. So 9 times x to the 1/2. And again, depending on what we want to do with this derivative, we might want to simplify this a bit. This would become 1 over 2 root x, and our second term would be 9 root x, just going back to the radical notation. Okay. So those are some examples of ones where you have to do a little bit of rearranging before you can apply those rules. All right. Last question I'm going to do here is a bit of an application here. For a bit of a thinking or a problem-solving type question here. At what points is the tangent to y equals 3 over the cube root of x parallel to x plus 16y plus 3 equals 0? So one of the things about solving questions like this is you have to get used to reading the questions and looking for the key calculus terms that sort of tell you what you need to do here. So some of the key terms in here are, I mean, if we're talking about the tangent in here, we know that this probably suggests that we're going to have to take the derivative. Because we know that taking the derivative of a function gives us the slope of the tangent. Over here, we got this word in here, parallel. Okay. Now, if we're thinking about slopes of tangents, what do we know about the slopes of parallel lines? Yeah, so we're going to have sort of the same slopes here. Okay. This is our function here that we're going to have to take the derivative of, and yeah, it's always a good bet to take the derivative of the function that you're given. From here to the end of the course, if you don't know what to do, take the derivative of the function, and that's usually good for a mark, you know. So we know we're going to have to take the derivative of this function. Now, what about this function over here? Well, we want something that is parallel to this thing here. Now we look at that equation and we can see, let's see, x plus 16y plus 3 equals 0. This is the equation of a line in standard form. So maybe the first thing to do here is to figure out what the slope of this line is, because we want these two things to have the same slope. So we should take this and we should put it into y equals mx plus b form, because that'll give us the slope. Okay, so let's start there. Let's bring, we'll keep the 16y over here, and we'll bring everything else to the other side. So that gives us negative x minus 3. And let's divide through by the 16. So that gives us negative 1 over 16x minus 3 over 16. So the slope that we're looking for is negative 1 over 16. So we want to find the points, so the value of x and the value of y, where the tangent has a slope of negative 1 over 16. So to start working on our tangent, we've got to take the derivative of this function here. So let's see, we've got y equals 3 over the cube root of x. I'm just going to write that as y equals 3x to the negative 1/3, which is kind of an easier form to work with in there. So we want to take the derivative of that. The derivative is what we're going to use to find the slope of the tangent. So let's see. How do we take the derivative of this thing? And then what is our new exponent going to be here? Negative 4 over 3. And then we can multiply this out. This gives us negative x to the negative 4/3. Okay. Or negative 1 over x to the 4/3. So this is our derivative, y primed. We want to know, because the derivative here represents the slope of the tangent, to our original function, we want to find out where the slope of the tangent here is equal to negative 1 over 16. So we're going to set these two things equal to each other. So we'll get negative 1 over 16. Write this a little neater. Negative 1 over 16 equals negative 1 over x to the 4/3. This is the equation that we need to solve. So how can we solve this thing? Richard. Yeah. Yeah. We can work just with the denominators because the numerators are the same. Okay, so we've got x to the power of 4 over thirds has got to equal 16. What can we do from here? All this knowledge from advanced functions, which is, Brody, what do you think? X to the 1.
So you would multiply, or you make x to the power, it would be 12 out, you could do 1, and then do that to the outside, because you're doing both sides. Or do you want to try and get rid of the power?
Okay, so you raise both sides to the same power that is going to get them to cancel out and give you 1.
Yeah.
Okay, so that's a good strategy. So the power I'm going to raise them to is 3 over 4 and 3 over 4, right? And that's what you meant by the 12. Yeah, because that'll give me 12 over 12, okay, which will just be 1. So that gives me x equals 16 to the 3 over 4. And then I can just punch that into my calculator and work out what it is. Now when we do that, actually we're going to want both the positive and the negative answers, because right here, this was x to the 4th root. So we could have a negative number in here and it'll make it positive. right? It's like, x squared equals some number, you get the positive and the negative answers. So we want both the positive and the negative answers that we get from evaluating that expression. What do we get when we evaluate that expression? You're taking the fourth root of 16, and then you're cubing it. The fourth root of 16 is 2, and then you cube it to get 8. So this is positive, negative 8. All right, so this is the solution to our equation. Are we done yet? Well, not quite. These are the x values where the slope of the tangent will equal negative 1 over 16. So the line will be parallel to the tangent will be parallel to the line that we were given. In the original question, it asked us for the points, which means we want both an x and a y value. So we've got to take these x values and sub them into our equation to get our y values. So our equation here is y equals, I'll just bring these guys up like this. Our equation was 3 over the cube root of x. Okay, so if we sub in x equals 8, y is going to equal 3 over the cube root of 8, which is 2. Okay, if x equals negative 8, same thing, 3 over the cube root of negative 8. Cube root of negative 8 is negative 2, so we get negative 3 over 2. And of course we get, okay, so we get 3 over 2 here, because it's 3 over the cube root of 8. And of course we get negative 3 over 2 down here. Right? What did I do wrong?
I don't know, but remember when you square root, you have the I? Yeah, it can't be negative inside.
I'm not square rooting it though, I'm cube rooting it.
Oh, you can do that?
Yeah, you can do that. Yeah.
Okay, hold on.
I mean, the cube root of negative 8, like if I do negative 2 times negative 2 times negative 2 gives me negative 8. So only even roots. Okay, so square roots, fourth roots, sixth roots, things like that. Odd roots, you're fine with that. Okay, they can be negative all they want. Okay, so what are the points? The points are, let's see. So we'll say, I don't know, therefore, um, 8, 3 over 2, and negative 8, negative 3 over 2. Okay. And that's how you do it. Okay. Now, I mean, what this thing looks like is, if we were to graph this, our function looks like this. Okay, which is a very crude sketch of it. So we've got 2 points, sort of one over here on this branch, one over here on this branch, where if we find the slope of the tangent, I mean, they're going to have the same slope of the tangent, and that slope is going to be negative 1 over 16. And because the 2 branches of the curve are symmetric, we've got, well, I mean, the 2 points, the coordinates of the 2 points are symmetric, right? And I should label this. This is, where is this? F at x equals 3 over cube root of x. Okay. All right.
So when you said something about like even numbers, is that what you did? Plus minus 8 over there? So
Yeah, that's why we got the plus minus over here, because I was doing an even exponent right here. So if I put a negative in here, when I do it to the power of 4, that makes it positive. If it's negative, if I put a negative in there, it makes it positive. If it's positive, I make it positive. So I could put either plus or minus 8 into this expression, and I get 16 out. So that's why I need positive and negative answers. Okay?